look at chapter 5, and you'll see that the homework problems are also all from the textbook from chapter 5. So we first want to find out where we use the aggregates and what are the important properties of aggregates and why do we care about them. And then we start with weight-volume relationships. And these are very important in both concrete mixed design and asphalt concrete mixed design. We won't repeat them then. So this is actually an important packet, an important lecture. So let's get started. Aggregates are everywhere actually. So these are some of the applications that you can see here. In pavement, we use aggregates as the support. You use the aggregates to support foundations, to support retaining walls, and of course, we use a lot of aggregates to make Portland cement concrete, asphalt concrete, and there are other applications, like for example, ballast. You have maybe seen the railway tracks. Underneath, you see big crushed stone ballasts. So what we need to find out is, for example, can we use any type of aggregates for any application? How would we choose? What properties of aggregates matter the most? Someone may say, well, in pavements, why do we use aggregates? Why don't we just use asphalt concrete all the way? If you had a way to see inside the pavement system, it would look something like that. Let's say if you have asphalt concrete, or if you have concrete on the top, what you see is only one relatively very thin layer. Underneath you have base, sub-base, and subgrade. And as you go down, as you go deeper, let's say if you are looking at the load from a truck, as you go deeper, this load gets more spread out and it becomes less in terms of magnitude. So we don't need to use concrete or asphalt concrete all the way down. Why do we use aggregate? The most important reason is the cost. It's much cheaper to use aggregates than to use asphalt concrete all the way. For example, in runways, if you had a way to see inside the runways, the asphalt concrete is much thicker compared to highways because you want to have better quality. You don't want to have any issues with the planes taking off and landing. But in highway, typically we are using tons of aggregates. So, here the font size kind of shows the importance of different reasons why aggregates are being used. So you see the largest font is which aspect? Economy, the cost. That is the most important one. And then it's the dimensional stability, because aggregates they can be angular, so you can use them to keep things in place. And then there are other properties. They are strong, they can be used as filler materials, they have good shrinkage and thermal properties. So again here, font size is basically telling you how important each aspect is. So you have to remember that kind of the most important aspect is economy. And in different applications, the importance of each aspect becomes different. You will see. So economy is a very important aspect, and then we have a stability, a strength, and the others are less essential. So where do we get these aggregates and how do we use them? So typically, we want to use local aggregates. This is essential to remember, because the cost of aggregates, you'll be surprised, the cost is actually pretty much the transportation cost. The aggregates themselves are relatively cheap. What costs is to transport them from one place to the other. And if you want to get a feeling of where they are being used the most is concrete. You remember concrete is the most widely used construction material, and about 85% of its volume is aggregate. So this is where we use it the most. Asphalt concrete, it should say asphalt concrete, comes second, and the others come afterwards. So just to get a feeling, this is how much you, in 2000, I'm sure it is much more right now. Anyway, where do we get it? Well, of course, we get it from the earth somewhere. And remember, we always want to get it as locally as possible because cost is the number one reason we use it, and transportation is the number one factor in making it expensive. So, local. And because typically everyone is using the local aggregates, if you go from one state to the other, for example, you have different properties, you have different types of aggregates, etc. So where do we get them? We said that we get it from the earth, the crust of the earth. If you kind of look at the crust of the earth, you have the topsoil and you have the bedrock. So one source of aggregate is when we just use pits. These are open quarries. There is no need to do any blasting. And because of that, it's the topsoil. These are low cost, but also low quality, because there can be anything. They can be mixed of different things depending on where you are. The better quality aggregates are when you kind of dig a little bit deeper and you crush the bedrock. These are more expensive, higher quality, and they require blast. And this is the source for crushed stone and manufactured sand. So basically larger crushed. We'll talk about them and you'll see why they're very useful in some of our applications. If you have any questions, ask me. This is descriptive, so I'm going relatively fast. So there are also other sources of aggregates. For example, we learned about the steel manufacturing. The slag that is skimmed off the top of the molten material, you can also get artificial aggregates from there. And it's a nice way to use some of the byproducts. So these are kind of recycled and manufactured materials. And in some applications, you want to have for example, very lightweight concrete. You can even use a styrofoam if it is not load-bearing. So this is kind of the natural versus manufactured materials. So you may have seen quarries. Has everyone seen at least one quarry? There is one in Le Mans, right? If you have ever driven there, everyone knows where Le Mans is. There is a quarry there. So the quarries may be open pit like that, on the ground, or maybe underground like here. There is also the possibility to get aggregates from the deposits around the rivers. Even you can get it from the riverbeds, as you can see here. From quarries, typically you get, especially the underground ones, you get crushed stone. And here you typically get gravel. And it turns out that if you get gravel from rivers, because they have been tumbling in water, they're much rounder. I mean, you have experience, you have seen rivers. If you look at the gravels, you never know. Gravels, they're kind of round and shiny, right? But if you look at quarry, they have to blast them, they have to cut them out. So they kind of come out edgy. And you'll see that these two types of aggregates have different properties, and we need them for different applications. So they're both useful. So that's what I was telling you about. If you look at the pictures on the top, what do you see? On one side, you are looking at gravels from the river bed, for example. On the other side, you are looking at crushed stone. Tell me two main differences that you see between these two pictures. One I just told you. What's the first one? Oh, that's actually the second one. So the first one I just told you, the gravel is rounded, right? If you look at the individual gravel, and if you go back to your memory of playing around river at some point in your life, you remember these kind of shiny gravel. And on the other side, you have kind of, this is what we call angular aggregates. And the other difference is just what your friend just said. It's the color. But what is exactly? One is colorful, the other is all the same color. So let's make it more technical. Gravel can have different, you can have a mix of different rocks in it. Because depending on the history, etc., you can have different things on the river. But crushed stone, you are getting the bedrock, you are crushing it yourself. So this can be heterogeneous. This can be very mix of different rocks. That means a mix of qualities. Quality is not the same. I would say variable quality. And here it's more or less uniform. And these are important properties. That means that's lower quality for us. You never know what you have. And then this is kind of one example of comparing natural versus manufactured. Again, remember, for example, a slag from the steel plants, you can use it as aggregates, which is a nice thing to do. You see the color is at least different, and the properties are different. Yes, please.
Crushed rock. I know it's a little bit bigger. The size and grain matters for the aggregate being used.
Yeah, crushed rock, you can control the size. Basically, you can decide how fine you crush it. What you get from the river, this is what you get. If it is too big, you have to crush it afterwards. Yeah. Good question. So if you haven't seen a quarry, and if next time you are driving in Le Mans, I encourage you to take a look into the dig, and you kind of take a look at it. This is the site you see. There will be blasting and crushing. Has anyone worked in a site like that by any chance? Something relevant to that? No? And just to make a comparison, so again, you may have seen the quarries. They can be very, very large. Later on, I'll show you some videos when we talk about cement, so you see really, they can be really, really huge. And this is one example of basically extracting the sand and gravel from river deposits. Also, it's interesting if you travel next time, maybe in summer, to pay attention how local aggregates kind of, you see them reflected in the highway. Let's say if you are driving in Utah, where everything is red, how many people have been to Utah? Right. You remember the redness. If you look at the roads, you see that the roads are actually also pink. And that is kind of an indication that people are using the local aggregates. It's kind of fun to pay attention to these details. Okay. So now we kind of want to learn about the properties. Now from introduction, kind of going towards more what properties of these aggregates matter. So you may remember from geology that there are three main types of rocks, and the aggregates are coming from some of these rocks. Aggregates are pieces of rocks. So you can have igneous, you can have sedimentary, you can have metamorphic, and you probably remember from geology that igneous are from the molten magma. Sedimentary is more like after many years of the deposits and cementation of smaller particles that have been deposited, and then metamorphic can be either types after going through high temperature pressure transformation. Of course, the properties of aggregates will follow the properties of the parent rocks. You will see, for example, in asphalt concrete, it matters what type of asphalt you have to use depending on the source of your aggregates. That's one example of importance of the type of rock they are coming from. In terms of properties, other properties, these are some of the properties that are important for concrete and asphalt concrete design: shape and texture, soundness, toughness, water absorption, specific gravity, strength, gradation, and whether they contain some other substances that can have reactions that we don't necessarily want with, let's say, cement. So we want to kind of go through each one of these properties. I told you a little bit about shape already. If you have gravel versus crushed gravel, or crushed stone, sometimes it's called. They are typically rounded, and these are angular. And these are typically what we call coarse aggregates. Coarse aggregates, this is in the context of Portland cement concrete and asphalt concrete. And that is when the size is greater than 4.75 millimeter. This is about 1.5 inch. How many are taking soil mechanics? What sieve size is it? What was it? 4, exactly. So if you are not taking it, don't worry. I explain what sieve analysis is. So no reason to be worried about not taking soil mechanics here. No issue. So that means that you all know what a sieve is, no matter what you are taking, soil mechanics or not. The size of the sieve kind of determines the number. We'll talk about it. And if it stays on the sieve size number 4, which has the size 4.75 millimeter, like kind of a square, then it's considered coarse aggregate for concrete mix and asphalt mix design. And the shape, it is pretty much defined by the source of the aggregates, as you talked about. And then, if it is less than that, in concrete design and asphalt design, this is considered fine. In soil mechanics, fine is much finer, right? It's smaller than sieve number 200. But here we just have coarse and fine. You don't need to know, you don't need to go that far. And we consider this sand. And of course, sand can come from natural deposits, or it can be manufactured, as you can see here. It's just a smaller. And here, for those of you who are not taking soil mechanics, this is how a sieve looks like. And basically the number is how many openings you have per 1 inch. And what else? Yeah, that's it. And the things I told you, it is also set here. Did I say it's not 4.75 millimeter, it's not 1.5 inch. It's 1/4 of an inch. Sorry about that. So we have coarse and fine. Any questions about that? Especially if you are not taking soil mechanics lab. So you assemble the sieves like that, starting with the larger size, coarser openings to the smaller ones, and then you put the material on the top and you let it go. Typically you vibrate it to make sure that nothing is stuck in any of the sieves, and then you weigh how much of the material is on each sieve. And this is how we find out about the gradation. The definition of coarse and fine in this class is really just looking at sieve number 4, which means you have 4 openings per 1 inch. That's the number. The size is 4.75 millimeter, which is 1/4 of an inch. What else? And then there are some important definitions. These are not some things to memorize. Depending on the mixed design standards, people have come up with different definitions. For example, for maximum aggregate size, sometimes it is really the largest sieve size that all the aggregates pass through. Sometimes it's the sieve size where 10% of the aggregates are retained on. You will see in concrete and in asphalt, there are different definitions. But nothing to worry about. It's written in the code. You just see it and you use whatever it is there. This is super pave, is for asphalt concrete design. The name suggests super pave for pavement. For example, maximum aggregate size is 1 size larger than the nominal, and the nominal is here. So it's kind of just having some particular definitions. What is important is that you understand the gradation curve, you understand how it is obtained, and we do a small example to make sure that everyone knows how to get that and how to read different things on the gradation curve. Any question so far? It's not difficult at all. So it's kind of repetition here again. So we can have coarse and fine. And I already told you that gravels could be a mix of different rocks, but crushed stone are a lot more uniform. So this is size. We go back to gradation a little bit later and we do some examples on that. How about shape? Here you see different definitions for different shapes of the aggregates. So we have angular, where you have many fractured faces. And then we have rounded. There is flaky, elongated, flaky and elongated. Why do we care about these? It's not just nice names. You will see later on that you have to limit, for example, flaky particles when you are using certain aggregates for asphalt concrete. Why do you think, for example, a flaky aggregate would not be a good aggregate to use in pavement? Just intuition. that okay, it doesn't stick to the other aggregates. It can, yes, that's one reason. And it's the same problem also is with rounded aggregates. Exactly. What else can happen if it is very flaky or elongated? Exactly, it can break. When you compact, it can just break. It's much easier to break in one direction. It can break. And something which is not very obvious to you right now is that they also have a lot of surface. This could be a good or bad thing depending on the application. It means that you need to have a lot of glue to glue things together if you have a lot of surface. So it makes everything more expensive. So if you are making asphalt concrete with a flaky aggregate, then you need a lot more asphalt, which is expensive to make the aggregate. So in terms of shape, you can have these different types that I just showed you. Elongated is when the largest dimension over the medium dimension is greater than 3. And when it is flaky and elongated, maybe I'll go back here. This is when the maximum over minimum dimension is greater than 5. But you may see different definitions depending on particular application. This is not set in stone in any ways. So they are not desired because of, as we discussed, they can easily break and it's hard to compact them. So what typically you like to have for asphalt concrete is to have angular and in terms of texture rough aggregates so that they can interlock, like someone here said, they can stick past each other, they can interlock and provide this stability that you need when the truck is going over the road you have designed. At the same time, sometimes in concrete, you want to have a little bit rounded and smoother because of workability. I'll tell you what that is in a second. So the point here is that you realize particle shapes are important. And you will see later when we design concrete or asphalt concrete, you have to have, for example, a limit on how much flaky aggregates you have, or you need to have a minimum amount of angular aggregates for asphalt concrete mix. Can we move? Everyone has written notes down. So in terms of texture and angularity, a lot of times people use really visual inspection and they kind of count the number of fractured faces depending on if you have none, one, or more than one. Nowadays they are hopefully soon moving towards camera-based methods, where they actually take picture and then they figure out if the aggregates are angular or not. But the traditional method is really looking and inspecting samples of the aggregate and counting how many fractured faces you have, and you decide on the texture of your aggregate. And there are even methods and ways to measure, for example, if you have elongated and flat. As I said, if you have this ratio greater than 3, it will be elongated. If this ratio is greater than 5, will be classified as flat and elongated. Again, in the old times, people would really use this kind of apparatus, very manual. You put the aggregates there and you check what are this dimension ratio. Now they're moving towards like camera-based, video-based, so you just look at the pictures and automatically try to figure out what is the ratio of the sizes. Civil engineering, some of these advances are going slower than you wish to see it happening, but I've seen them. Even PennDOT now has camera-based, and that's for coarse aggregates. For fine aggregates, that is difficult, as you may imagine. You can't look at the fine aggregates and see if they are round or angular. So what you do is you put some fine aggregates here and you drop them from a certain distance into a cylinder, and then you weigh it. So the idea is, if everything is very round, then, or if it is angular, it's going to come together in a different way, and the amount of void would be different, so you would have different volume. So it is different if you drop particles which are like that inside this cone, or if they are very angular and they will not sit nicely over each other. You measure, it's the same volume, you measure the weight, and there are some tables that can tell you if the weight is between this and that, the percentage of angularity is this. This is kind of a very approximate way to find out how angular are your fine aggregates. I told you that for concrete, sometimes we would prefer a smooth and rounded aggregates, and it's because of workability. And workability of concrete, it means how easy it is to work. How many of you have ever poured concrete or mixed concrete? Yeah. So you have seen that, it is kind of a little bit like cooking. You need to have certain workability for it to easily vibrate and mix. So you can imagine if you have a lot of angular aggregates, it would be hard to mix it, to vibrate it. And more importantly, when you pour it into the mold, it would be hard for it to take the shape of the mold. So work here means mixing, pumping, placing, and finishing. And we typically want to have nice flow because you need less vibration. Some concrete, they are self-consolidated, and angular aggregates, if you use them, you can also achieve workability, but you need to add a lot more water. So you will see in concrete mix design that we need to limit the amount of angular aggregates in concrete. So try to fill this up now on your own based on the things we talked about. You can talk to each other. If everyone look up hair or his homework, is it graded? I passed around graded homework 6:30. Oh, this is too long. Ryan Harp is not in the class? No? Okay. So what should we write in the first box? Rough, angular, and elongated aggregates cause more friction, right? Second box, it's also more. For better workability, it is just like a soup. If you put more water, it's easier to mix. That's as easy as that. Aggregates are like, what, pieces of meat in a soup, or maybe potatoes, I don't know, depending on the soup. Similarly, in asphalt concrete, this has to be asphalt concrete. Angular aggregates require, so this is bitumen or bitumen. This is another word for asphalt. Does it need more or less asphalt if you have angular aggregates? What do you think? Less? Why? It's not about compaction. So when you have asphalt concrete, you haven't seen this. It's just, if you have asphalt concrete or concrete, what you have, if you have aggregates and you glue them, in concrete you use cement, in asphalt concrete you use asphalt binder. So now the question is, if you have angular aggregates, do you think you will need more asphalt or less? Idea? How many say less? How many more? Okay, it is more, but why? Does anyone want to argue that? Why? You want it?
There's more surface area.
Exactly. Whenever you hear something about that, just think about surface area. The same size aggregate, if you have a lot of edges, you have more surface area. It is just like gluing. If you were to glue two pieces, you would need to have more glue if you have more surface area. So this is exactly that. Angular aggregates may give more or less strength. If you have angular aggregates, do you think you will have, and you have them together compacted, and you have rounded aggregates, compare them, which one gives you more strength? Think this way, if you had a pile of angular aggregates, angular means like big faces or fractured faces, and rounded. If I ask you to step on one or the other, you have the choice. Which one would you step on? Which one? Which one? You would step on the rounded? What would happen if you step on the rounded one? I'm sorry? You like to skip. Does everyone follow? If you have angular aggregates, they interlock. So one aggregate interlocks to the other. So this interlocking prevents friction, it creates friction, prevents the slip. If you have a lot of, you should have this experience. If you have a pile of marbles, in the extreme case, if you go over it, the whole thing is going to roll down, right? You have no friction. You don't want to go on top of that. And flat and elongated aggregates should be kept to a minimum. Try to reason for yourself why, based on what we said. They easily break, and they're hard to compact. We are coming back to these concepts a few times later. Don't worry if you don't know much about concrete, etc. That's not a problem. Now, which one of these are incorrect? There could be more than one. Again, talk to your friends. See based on what we talked about. A, is it correct or incorrect? It's correct, right? If you have different rocks, you can have different properties. B, riverbeds are the main source of crushed stone. It's incorrect. What is the main source of crushed stone? Exactly, correct. C, use of angular aggregates can reduce the workability of concrete. Correct or incorrect? Exactly. Beach sand is usually not a desirable source of sand for concrete due to high salt concentration. This is correct. We haven't talked about it, but I guess intuition helps. Okay, we'll stop here. And next time we do weight-volume relationships.